In this lecture, we will discuss the concept of strong scaling, introducing first a motivating example for the runtime of a program, and then develop a model for the scaling of that program when given more computational resources, namely Amdahl's law. Finally, we will discuss some limitations and challenges of strong scaling and Amdahl's law in particular. If we have a program, and we have done our due diligence in parallelizing what we can measure the performance of the program as a function of the number of processors used. For a fixed problem size, we would anticipate, perhaps hope, that the commitment of additional resources will result in an increase in performance manifesting as a reduction in the execution time. This relationship between the number of processors and execution time for a fixed size problem is known as strong scaling. Let's imagine a program that performs a calculation which is very expensive, compute-bound, and amenable to parallelization. We can measure the performance of this program by observing the runtime as a function of the number of processors used. On a single processor, the runtime of the program is 10 hours. If we run the same program with two processors, for example, by splitting the computation of the arrays into separate MPI processes, we would expect the runtime to be ideally half of the single processor runtime, or 5 hours. In practice, this is rarely so. In our imagined scenario, the runtime might be closer to 6 hours. If we double the number of processors again, we might expect the runtime to be half of the two-processor runtime, or 3 hours. However, in practice, this is also unlikely to be the case. In our imagined scenario, the runtime might be closer to 4 hours. Repeating these experiments forms the backbone of a strong scaling study. Understanding this behavior, the relationship between the program runtime in terms of the resources used, is the fundamental question of scaling analysis. We will discuss two terms in this lecture, speedup and efficiency. We define the speedup as the ratio of the runtime of the program on a single processor to the runtime of the program on multiple processors. For example, if the runtime of a program on a single processor is 10 hours and the runtime of the program on two processors is 6 hours, the speedup is 10 over 6, or 1.67. We've committed twice as many processors to yield a reduction in runtime which is less than the ideal reduction, 1/2. Likewise, if the runtime of the program on 4 processors is 4 hours, speedup is 10 over 4, or 2.5. So we have dedicated 4 times as many resources for only a runtime reduction factor of 2.5. This comparison between the ideal speedup and the actual speedup is known as the parallel efficiency of the program, as distinct from the efficiencies we've discussed in other contexts. Thus, for the 2-processor case, we would compute an efficiency of 1.67 over 2, which is 0.83. For the 4-processor case, we would compute an efficiency of 2.5 over 4, which is 0.625. Ideally, we would have a precise correspondence between the reduction of the runtime to the number of processors, an efficiency of 1. In practice, this is not so, for good reason. We can express these concepts concisely and precisely as non-dimensional quantities. If we denote the runtime for a problem on P processors as T of P, then the speedup is written as S of P equal to T1 over Tp. The ratio of the single processor and P processor runtimes. Likewise, the efficiency is written as E of P equal to S of P over P, or the ratio of the speedup achieved with P processors to the commitment of those same resources. Measuring and expressing these quantities is one thing. By modeling the speedup or efficiency, we can analyze and understand the performance of our codes. In 1967, Gene Amdahl published a paper in which he described a model for the speedup of a program as a function of the number of processors used, known as Amdahl's law. Consider the distribution of runtime in a program. Initially, there is some setup which is likely to be essentially sequential, followed by most of the computational work which might be parallelized, and then perhaps some final work to clean up the data, again sequentially. We can then recognize when running this program with more processors, putting aside the possibility of a complete algorithmic rewrite, entails reducing the runtime of the parallelizable portion but leaving the sequential runtime untouched. This is the essential insight of Amdahl's law. The speedup of a program due to parallelism is limited by the fraction of the program runtime spent in inherently sequential operations, which we denote by the serial fraction f between 0 and 1. This is, importantly, a parameter of the program structure, an aggregation of the constraints posed by the logical ordering of the computations, and something one typically determines experimentally. Concisely, let the serial runtime be denoted by T sub s, and the parallel runtime be denoted by T sub p. The total runtime of the program with these distinct sequential and parallelizable regions is given by the sum of the sequential and parallelizable runtimes, or T is equal to Ts plus Tp. Since the sequential portion of the runtime is unmodified with increasing numbers of processors to linear order, then we may rewrite the sequential contribution to the runtime as a proportion of the single processor runtime. T sub s of p is equal to f dot t of 1. Likewise, for p equal to 1, T sub p of 1 is equal to 1 minus f dot t of 1. If the program is parallelized on p processors, then T sub p at best scales inversely with p. T sub p of p is equal to T sub p of 1 divided by p. Combining these ideas, we may predict the total runtime of the parallel program on p processors by adding the sequential runtime on one process to the parallel runtime on p processes, or T of p is equal to f dot t of 1 plus 1 minus f dot t of 1 over p. Amdahl places a pessimistic upper bound on the speedup achievable by straightforward parallelism, that is, without algorithmic or structural redesign of the program, based on the serial fraction. Expressing the speedup according to our model of the total runtime on p processors gives s of p equal to t1 divided by t of p is equal to 1 over f plus 1 minus f divided by p. This predicts a speedup between 1 and p for s of p, depending on s between 0 and 1. The smaller the sequential proportion of the runtime, the greater the possible speedup may be achieved with sufficient resources. Similarly, the efficiency of the parallel program on p processors is given by E of p equal to S of p divided by p, which is 1 over f dot p plus 1 minus f. This predicts an efficiency between 1 over 1 minus f and 1, depending on f between 0 and 1. The larger the sequential proportion of the runtime, the worse the possible efficiency. When f equals 0, then Amdahl's law predicts perfect scaling for arbitrarily large p. Now, no real computer has infinite processors, and no real computational problem is completely divisible. Thus, we leave the ideal case as an exercise for the viewer. Amdahl's law takes on a parsimonious form when plotted in log-log scale. That is, log of p against log of the speedup for non-zero f. For small p, we simply retrieve a linear relationship between log p and log of the speedup with slope of 1 minus f. While for p approximately 1 over f, this relationship transitions to a flat region where s of p goes to 1 over f, as p diverges. This shape may remind the viewer of roofline analysis. Indeed, the mathematical abstraction is fundamentally the same. We are describing the transition from exponential response to saturation. There are 4 intuitive observations resulting from this simple visual analysis. First, the speedup of the program is approximately linear for small p with a slope of 1 minus f. Second, for large p, the speedup approaches a constant value of 1 over f rather than continuing to increase. Third, we could identify an approximate number of processors beyond which the speedup no longer increases significantly. That's when p is approximately 1 over f. Fourth, the speedup is always less than p, even for very large p. Similar corollaries apply for the efficiency. These are left as an exercise for the viewer. Amdahl's law makes several assumptions and simplifications which limit the realism of the predictions produced by this model. Firstly, we assume that the sequential and parallel program calculations are easy to distinguish, and that the former is unmodified by the parallelism. Likewise, we assume that the parallel execution has no overhead, for example, communication, by taking T sub p of p equal to T sub p of 1 divided by p. Finally, we assume the workload can be divided into arbitrarily small chunks as p diverges to no ill effect. Likewise, Amdahl's law does not rely on a hardware model. Impacts on the actual runtime due to the realities of actual computing are not accounted for. For example, it is not uncommon to measure superlinear strong scaling for some problems where S of p is greater than p due to hardware effects like cache-level boundaries, which are not realizable within Amdahl's law. Likewise, for very many processors, we may find a worse outcome than Amdahl's law of diminishing returns. Indeed, we may find that the overheads of parallelism cause an asymptotic slowdown compared to Amdahl's law. Further, Amdahl's law assumes that the sequential portion of the runtime is unmodified by the parallelism. In practice, this is often untrue. Amdahl's law is a simple model for parallel program runtime that relies on simplifying assumptions to place a pessimistic upper bound on the realizable parallel speedup determined by the sequential fraction of the program runtime and the available resources. It provides a simple model for understanding and analyzing the strong scaling of parallel codes, and thus is an essential tool in the skill set of those practicing high-performance computing. Thank you very much for watching, and I'll see you in another lecture.